Good evening, everyone. Welcome to class 11 of stochastic communication. Stochastic control and communication. So, uh, basically, I'll do a quick recap of what we did last class. So, we were talking about decision-making problems, right? And in the decision-making problems, we had one problem was uh, so first we saw all the policies, how to model decision-making problems using MDP model or a stochastic control model. Then we saw the principle of optimality, and using this we defined the dynamic programming to find an optimal policy to find an optimal policy to solve these types of problems. Before this, we saw different types of policies. We saw different types of policies like Markov deterministic, Markov random, history deterministic, history random, and also stationary policies. Then out of these policies, we took Markov deterministic and the given algorithm for dynamic programming of how to solve for Markov deterministic problems. We saw the inventory control problem, and we solved this using dynamic programming. Okay. Next, we saw the optimal stopping problem, which was not similar to the inventory control problem, but we modeled the optimal stopping problem as an inventory control problem. Sorry, not as an inventory control problem, as an NDP. We modeled this as an NDP. And used dynamic programming to solve it. Okay, in the optimal stopping problem, we gave an example of the secretary problem. We solved the secretary problem using dynamic programming. We saw that the answer was to secretary problem was stop after you reach 1 by E10, which is approximately equal to 36.8% of candidates. And then you look at 36.8 candidates, and after that, if someone meets your threshold, then if you meet the best candidate after that, you accept it. Okay? So these were our decision making problems. So today we'll see about linear systems and quadratic cost problems. Right. So when I mean linear systems and quadratic cost problems, what I mean is the dynamics of the system are linear and the cost function is quadratic in state. Okay. Cost function is quadratic in state. Okay. So when I say that the dynamics is linear or I have linear dynamics, I mean that the dynamics are followed by a sorry xk plus 1 equal to ak xk plus bk uk plus wk, where ak, bk are matrices of appropriate dimension. Okay. Mm, Your xk is your state vector at time k. Uk is your control vector at time k. So basically, this is your action. Uk is your action. Xk is your control vector. Wk is the randomness or the random vector. Is also known as noise in the system. Right? And xk plus 1 is your state vector at time k plus 1. So this is how your function, the function xk plus 1 equal to f of xk uk wk. So when I mean linear data system, I mean that f is linear, right? We'll make some assumptions on the noise. So one assumption is they are IID and their mean is 0 and they have some finite variance is finite. Their variance is finite. So this means their variance is finite. This is their mean is 0 and they are identical and independently distributed, right? Okay, so this system has all the qualifications to model it as the stochastic control model that we were modeling till now. So basically, you have your time scale from 0 to n and discrete time instances. So at xk, you know the value of xk. So you know the value of xk. Now you choose uk. Knowing this value of xk, you choose uk. Once you choose uk, you're affected by noise wk in the environment, which makes the transition to xk plus 1 based on this linear dynamics. Now at xk plus 1, knowing xk plus 1, you choose uk plus 1. And then in the time interval k plus 1 to k plus 2, the system undergoes noise of wk plus 1. This wk plus 1 you don't know. You just know statistics of the wk plus 1, right? Then you get to a transition k2 plus 1, which is xk plus 2, right? So you want to choose UKs. Now, how do you want to choose the UK? You want to minimize some objective. So that objective is given by minimize pi belongs to pi m such that expectation of xn transpose qn xn plus summation k equal to 0 to n minus 1 xk transpose qk xk plus uk transpose rk uk. So what does this mean is this is your terminal state cost This is your stage-wise cost of visiting state xk, and this is your control cost, or in layman terms, it's the energy that you have spent to add the control of UK to the system, right? And this control cost is at all time steps, because this is at all time steps you are taking a decision. This is your state cost, the cost you pay for visiting a state. And this is your terminal cost at time step n. Because it's a finite horizon problem, we are looking only till horizon n. Okay. Some more assumptions in this cost function are that your R at RK matrix is a positive definite matrix. Right? This is a positive definite matrix, and your QK is a positive semi-definite matrix. These basically allow you to come up with the objective function to be convex, right? And also you can see that the objective is quadratic in nature. So here you have x square, here you have x square, and here it is u square, but then we don't know how does u depend on x. We don't know if mu of x is equal to u. This, is it linear or is it uh, quadratic? We don't know this, but this is quadratic in u square, this quadratic in x square, this quadratic in x. We have to find what the policy and the what the decision rule at each time step is going to be, right? So these types of problems, right? These types of problems are basically known as linear quadratic regulators. So why are they called as regulators? Are because so the linear and quadratic is because the dynamics are linear and the cost function is quadratic. Regulators because you want to follow a trajectory, right? So when you try to follow a trajectory, it's known as a regulator. So suppose you have a given trajectory where suppose x0 bar, x1 bar, and so on, xn bar. This is your given trajectory. Okay. So if you try to minimize expected xn minus, sorry, this xn minus xn bar transpose qn xn minus xn bar plus summation k equal to 0 to n minus 1 xk minus xk bar transpose qk xk minus xk bar plus uk transpose rk uk. So then basically what you're doing is you're trying to minimize this is the terminal cost, and this gives you a notion of how far you are from xn. So this is where you are. You want to calculate how far you are from xn bar. So you want to minimize this distance as small as possible. So this quadratic function will let you to minimize the distance between the trajectory that is given and the trajectory that you take by choosing these UKs. Okay. Similarly, here also, this is the cost is incurred because you you are straying away from the trajectory, and the farther you stray, the more cost you pay. So ideally, you would want to be as close to the given trajectory as possible, right? But as you see, there are Qn and Qk. So basically, these are skewed distances, not normal distances, skewed distances. You can make Qn to be identity, Qk to be identity. If they're identity, then they're obviously positive semi-definite. So you can make the Qns to be identity, and then get just the exact distance. But if you want some skewed distance also, you can put them in cost, right? It depends on what problem you're solving for. The cost function, you can change these Qns and Rks, but they need to be positive definite or positive semi-definite. Okay. So now what we'll do is we'll use dynamic programming to solve the above problem. Not the linear quadratic regulator, but the linear systems and quadratic cost problems. So to use dynamic programming to solve these linear systems and quadratic cost problems, basically you first look at t equal to n, and then jn xn equal to xn transpose qn xn for all xn. Okay. Then we write the equation for t equal to n minus 1. So jn minus 1 xn minus 1 is equal to, so I'll write this here, min over un minus 1, such that you're minimizing the expected cost. And expected cost here is stage-wise cost plus the previous cost. So stage-wise cost is xn minus 1 transpose qn minus 1 xn minus 1 plus un minus 1 rn minus 1 un minus 1. So this is transpose, right? Plus jn, and here you'll have xn, right? But xn, we know the dynamics. The time This is a function of xn minus 1 and not xn. So this is basically uh, an xn plus bn un plus wn, right? And this expectation is over wn because this is the only thing random. So this becomes min un minus 1 expectation of xn minus 1 transpose qn minus 1 xn minus 1 plus un minus 1 transpose Rn minus 1 un minus 1 plus Jn an xn plus Bn un plus W. But what do we know about Jn of any function? Jn xn is of this form, right? So we'll replace this here. Then we'll get minimize un minus 1 expectation xn minus 1 transpose un minus 1 xn minus 1 plus un minus 1 transpose Rn minus 1 un minus 1 plus an xn plus bn un plus wn transpose un into an xn plus bn un plus wn. So as you can see, these two terms are not random. Right. So I can take this out of the expectation. The only thing that random here is this wn and wn. So these both are random. So I take the non-random terms out. I get xn minus 1 transpose un minus 1 xn minus 1 plus un minus 1 transpose rn minus 1 un minus 1 plus expectation of an xn plus bn un plus w1 transpose qn an xn plus bn un plus w, right? Now here also, if you see, this term and this term is not random. So I can actually expand this out and take out even more not random, not random. And I can expand this term even more and take out the stuff which does not need the expectation, which are just constants or which are unknowns, right? This term does not This term does not depend on this is not a random term. So but you'll have a term where plus expectation an xn plus bn un whole transpose qn wn plus expectation of wn transpose qn w, right? You'll have these three terms. So from the assumption that the mean of wn is 0, this is 0, right? And this is just a variance term of the noise, but then this does not depend on un minus. Therefore, I can just eliminate this from the minimum, and I can write this as minimum un minus 1 xn minus 1 transpose qn minus 1 xn minus 1 plus un minus 1 transpose rn minus 1 un minus 1 plus an minus 1 xn minus 1 plus bn minus 1 un minus 1. Okay, I think I might have made a mistake here. So these all are n minus 1s. These all are minus 1s. Plus bn minus 1, bn minus 1. Right? The cost function would include this function, but this doesn't depend on un minus 1. Hence, I'm just minimizing these three terms over un minus 1. Now, since this is a quadratic term in x, and this is also a quadratic term in x, basically what we want to do is we want to differentiate the objective function and put gradient equal to 0. gradient with respect to un minus 1 equal to 0. Put gradient with respect to un minus 1. Find this and put that equal to 0. So if you do that, what you get is, so this is 0. So here you will get Rn minus 1 un minus 1 plus here you will get 1. So Bn minus 1 transpose Qn Bn minus 1, right? So basically these two terms. So Qn plus Bn minus 1 transpose Qn and An minus 1 Xn minus 1 Un minus 1. Oh, no, sorry. Because of differential with respect to, so you'll get these three terms. So this and this and this. So the blue term would be give you this. The pink term, underlying terms multiplied would give you this. Like these are your different after multiplying and then taking the differentiation. So we want this to be equal to 0. Now if you simplify this, you get Rn minus 1 plus Bn minus 1 transpose Qn Bn minus 1 into Un plus Bn minus 1 transpose Qn An minus 1 Xn minus 1 equal to 0. And now we want to find Un. Right. So Un equal to minus Rn minus 1 plus Bn minus 1 transpose Qn Bn minus 1 into Bn minus 1 transpose Qn An minus 1 Xn minus 1. So this is your optimal decision, right? So what have we found here is we have found the optimal decision rule at time n minus 1. And what we have seen is this optimal rule, one observation is this of the form ln minus 1, xn minus 1, where your ln is basically the whole of this term is your ln and you have xn minus 1. So your control is a linear function of xn minus 1, right? So if you want to find the cost that you have incurred, if you put this back, this whole thing back and calculate the cost, right? Then what you get it, so you get it in the form of xn minus 1 transpose kn minus 1 xn minus 1 plus expectation of wn minus 1 transpose qn wn minus 1. Okay. So, and where kn minus 1 is an minus 1 transpose qn minus qn bn minus 1 bn minus 1 transpose qn bn minus qn minus 1 bn minus 1. Sorry. n minus 1, Vn minus 1 plus Rn minus 1 whole inverse Pn transpose Qn into An minus 1. So if you observe this Kn minus 1, what you'll see is this is symmetric and it's also positive semi-definite. If you consider under the assumption that Rk and Qk are positive semi-definite. Rk is positive definite and Qk is positive semi-definite. Okay. So now the observations that we make from here is we have seen that Jn Qn is of the form Xn transpose Qn Xn, right? This is convex and yeah, this is convex. Similarly, if you write Jn minus 1, so this is Xn, Xn minus 1, this is Xn transpose Kn, Xn minus 1 plus expectation of Wn minus 1 transpose Qn Wn minus 1, right? And here also you can see that it is quadratic in X n minus 1, right? And because and also convex, and because this quadratic nature keeps on continuing, so basically every time you keep on substituting, so okay, so here the optimal policy was linear because your cost function was quadratic and it was quadratic, but then here you had a bilinear term of u and x, but u was because the optimal policy u is linear uh, function of x. So if you substitute u as a linear function of x, this whole thing becomes a quadratic cost function in x. So jn minus 1 is again quadratic in x. Here also it was quadratic. So because the optimal policy is linear, again it becomes quadratic. So again, if you substitute this back to jn min and calculate now for t equal to n minus 2, at t equal to n minus 2, if you calculate jn minus 2 xn minus 2 as min un minus 1 expectation xn minus 2 transpose un minus 1 xn minus 2 plus this is minus 2 un minus 2 transpose rn minus 2 un minus 2 plus jn minus 1 a n minus 2 xn minus 2 plus bn minus 2 un minus 2 plus wn minus 2. And now since this is quadratic in x, this is quadratic in x, and now you have this whole term where you will have a quadratic in x term. So if you take the derivative and put it equal to 0, then your optimal un minus 1 is linear. In the same way that we had un minus 1 linear here. And hence you can write un minus 2 star as ln minus 2 xn minus 2, right? So what we have seen here is for all t, mu t star of xt is of the form lt xt. And this lt can be calculated iteratively. So how do you calculate lt iteratively is you take lt equal to minus bt transpose kt plus 1 dt plus rt whole inverse bt transpose kt plus 1 dt and kn equal to qn, and kt is equal to at transpose kt plus 1 minus kt plus 1 bt transpose kt plus 1 bt plus rt whole inverse bt transpose kt plus 1 kt plus qt, right? This is known as the Riccati equation, and this is known as the Kalman gain. And you can these all does not depend on the noise. This just depends on kt, at, bt, the system parameters, and qt and rt, the cost function parameter. So if you know at, bt, rt, qt, then you'll be able to calculate all the values of kt in recursive form from kn equal to qn, right? And if you know all the values of kt, then you'll be able to calculate the Kalman gains. And the optimal cost that you get, J0 x0, is basically x0 transpose k0 x0 plus summation t equal to 0 to n minus 1 expected wt transpose kt plus 1 wt. So here also you see that this is quadratic in initial state, and these are basically variance of noise at each step. So this term, the cost depends on noise. Whereas if you see the optimal policy, this does not depend on noise. So this is a observation that we have made here. And basically what is happening is you have linear dynamics and quadratic costs. So because your cost is quadratic, you have optimal linear policies. Because of linear and because you have optimal linear policies and you have linear dynamics, your cost again becomes quadratic. So because of this nice dependence, you have this sort of structure. And one more observation is the cost function, the optimal cost does not depend on noise. Hence, if you make noise to be zero, like everywhere, and uh, and then you solve the same problem, this would remain the same. The optimal policy would remain the same. Just this term would go to zero. The cost that you incur goes to zero. Because of the noise, the cost that you incur is basically the variance keeps on adding at each and every step because of the noise. So the observation is the optimal policy for the noiseless problem is optimal policy for the deterministic problem. This is not always true, and this is only true for this following case, like under these assumptions, right? And so there is one more approach to solve the stochastic control problem. That is, uh, you have a noisy problem. What you do is you replace the noise by its mean and make it a deterministic problem. You find the optimal policy, and the policy is optimal for noisy problem. So this equivalence of problems of making the deterministic problem equal to the noisy problem by just replacing the noise with its mean is true for LQR problems, as we saw above. But are there any more general problems for which it is true, right? So this equivalence is known as certainty equivalence problems. And we know that this holds for LQR problems. But are there any more general problems where this holds? We know that this does not hold for all the problems because we saw in the case of risk problems, you need to include all the other moments. You need to include all higher moments of the noise in the cost function. And that gives you an accurate representation of a real life problem. And the moment you include all the other higher moments, you will see that the optimal policy changes as how many moments you have introduced. Those many moments, the optimal policy will keep on changing, right? If you just introduce the mean, you'll get one optimal policy. If you introduce mean and variance, you'll get another. So this method of finding equivalence by just replacing the noise with mean or replacing the noise with mean and variance is certainly true for some subclass of problems, but um, what other problems are there such that this certainty equivalence problem theorem also holds? So that's it for today. In the next class, we'll see history related dynamic programming for history related problems and compare it with dynamic programming for Markov deterministic policies that we have seen, right? We have seen these. So we'll compare history dependent and Markov.